We're going live.
We're going,
There.
and hopefully we have audio. Looks like we have audio.
Mhm.
Live. Fantastic. In front of row G, guys. You in row H and back. Sit in front of row G. We're all talking to each other. Come on down in front of row G. And this is every day. And let me tell you, every day, you guys in front of row G. I think you're in H. You guys back there. Check your rows. And in front of G, please sit next to somebody and say hi, for goodness sake. In front of row G, you two in row H, in front of row G, please. Say hi to somebody. We're talking. You'll be talking to your colleague. You are not allowed to be antisocial in Chem 1. If you're in Chem 1, that's not an option. Front row G, please. Okay, we're about ready to get started. How's the audio? How's the audio? Can you guys all hear me? In front of row G, please. You guys are in row H. Come down and sit by somebody and say hi. We're all talking to each other all semester long. 8 weeks. So welcome. Here it is, Chem 1A, summer 2023. My name is Mark. I'm your host. We'll be spending 8 weeks together. It's going to be a crazy 8 weeks of instruction. We're going to do 16 weeks worth of chemistry in 8. So you'll be working really hard and really fast. If you have not done so, get Poll Everywhere running on your device and log in with your Berkeley ID and join this course. If you've read the course information, that's how you get credit for attendance. You can look at how that works on the course information page, how all aspects of the course work. In front of row G, please. A couple things. So for many of you, this might be your first college course. So let me just give you some ground rules of how it works here at Berkeley. It'll be different from high school. I will not stand here and work problems and hold your hand and go through things with you. My job, there's 3 parts to the course. There's the lecture, there's the discussions, and then there's the online work that you do. My job is to inspire you to go do those other things. Front row G, please, you guys coming in? I'll be here to give you the big picture and how everything fits together. That's what lecture is for. We will be doing interactive learning in lecture. That's what that's for. We're going to talk to each other. That's row H, sir. what you want to be able to do is come to lecture, you get credit, you respond with your poll everywhere, and we will be discussing chemistry. In front of row G, please. We're going to talk to each other, guys. Sit close, say hi to someone. So the second part of the course, so that's what lecture is for, inspiration and interactive learning. The second part of the course are the discussions. In the discussions, you will work out actual homework problems. You'll see it happen. So that's something, that's where that happens, where you do specific grinded out work. Discussions are also where you'll see some additional course content that will help you through the course, and your student instructors will generally lead the discussions. There's two different kinds of discussions. There's the discussions held here in Pimentel on Monday and Wednesday, I think, at 11 or something. Look it up. Those are recorded, so you'll be able to see those online. The others, that's row H, guys, who just came in. That's row H, please, in front of row G. We're going to talk to each other. So the, where was I? The discussions in this room will be recorded. But there will be other discussions that have not been posted yet because we have not met. Your student instructors aren't even here. They're in training right now. So when we meet them tomorrow, they will each choose a time in addition to Monday and Wednesday to have discussion sections. Those won't be recorded, but there'll be other opportunities for you to attend. For instance, if you can't make the Monday and Wednesday, or some of you might want to attend more than one. Some of you should get to know a student instructor. They are your main teacher, essentially. There's a lot of you. You can't all talk to me, but we have 5 student instructors, and we have 2 senior staff. And those are the people where you can get in and say, how does the course work if you're confused about something administrative, or especially, how does the science work? You can absolutely ask me questions anytime you can get a hold of me. I'll have an office hour every week, and I'll probably do one of the discussions. You can ask questions anytime in this forum, of course, but anything you ask me should be science. So don't ask me about administrative stuff with the course. Figure that out online or ask your student instructors. Those of you just coming in, sit in front of row G, so you'll have to cram in, say hello to somebody. Maybe you should come all the way down front or something. Say hello to somebody. We're going to all talk to each other in a minute. That's part of the class discussions. We talked about them being recorded versus live. We have something called Ed Discussion. It's on the website, and on the website, and that is how you will talk with your colleagues and peers and us. I will look at Ed Discussion. You ask science questions there. It's a fantastic resource because people in your in the class will help answer questions for you. So again, it will be some peer interaction. You'll probably get to know people. Some people become famous on Ed Discussion. Last summer, I think it was last summer, there was a student in the class that just answered everybody's question before I got to it. It was fantastic. But no one knew who, she put her name, but she didn't come to class. So we didn't know who she was. I didn't believe she existed. But that's a possibility. So use this. It's a fantastic and it's monitored every day by staff, one of the senior staff as well. So we can't introduce the staff due to union constraints. They're not here today. Midterm Friday already. This class goes very fast. There'll be a midterm. You notice on the syllabus it's called a mini midterm. It's not worth as many points. It's a chance for you with relatively low stakes. It's not the full 250 points. It's half of that. To get used to taking a college chemistry exam, especially one in Chem 1A, where you will be able to kind of practice at lower stakes. That'll be Friday evening online. Sit in front of row G, everybody please. So that is it, the preliminaries you've seen. I hope you've all seen this on the website. This has all the lecture material. You have the slides there that I'm going to show you if you want to download them in advance or paste them into your tablets to take extra notes. It will have the recordings of the lectures as soon as we get them posted, hopefully the same day. We're streaming live to YouTube right now. So if you go to the YouTube channel, a version of the lecture will be available immediately, essentially, or live. In front of row G, sir. In the back. In front of row G. So go there. All the course materials there. Your reading is there. We have links to reading material. There's no required textbook. Please feel free to, if you don't like the reading we provide, to use Google and learn about stuff on your own. But refer to the reading we give you because we know that's correct. And I don't know if you've been on the internet, but there's some stuff out there that isn't. So use ours as the gold standard, the stuff we provide you online. Okay, did I get everything? Is that about it?
Homework.
Oh, homework. Yes. Homework are all done online. Your exams are all done online. The homework come from a huge bank of questions. And they're randomized, so you'll get different ones every time you take it. We keep your highest score on homework, even if you do it multiple times. Your highest one is recorded, so you can take it as many times as you want. Your highest score is recorded, and it will not change. The exam questions also come from the same bank. 70% or more of the questions you see on exam will come from the same bank. So what does that mean you should do? Do the homework until you see the same questions over and over, and then you'll know you have seen them all. So practice, practice, practice on the homework. Do them over and over until you can do all the questions that are there, and you will see then those questions again on the exam. They will change slightly as it might be different numbers, of course, or maybe on the homework question, we asked you about a trend going up, and we'll ask you about the trend going down, but the question will look very much the same. But read it carefully, because the trend might have changed. So be careful not to answer exactly how you answered in the homework, just in case. You should look carefully at the problems. Okay? I think that's the administrative stuff to get out of the way. Day one, we will plunge more or less right in. First, we'd like to get to know each other a little bit. Every day, we will put the learning goals up on the start of the lecture. Today, when we're doing this introduction, there isn't really a learning goal to the stuff we'll do right now, but we should know this. Ignorance just means I don't know, and I don't know is the foundation of science. You go into a question understanding that you don't know what's going on, and try to learn from nature and not any preconceived idea that you have. So it just means open-minded is what science is about. And if you ever see something that contradicts what you think in nature, then you have to consider that. We always don't know. Even our most advanced theories in science are always challenged. We're always learning. There is no I know in science. There's only I don't know and I keep learning. So let's learn about you guys. You can touch the screen, I hope, when I do that. Oh, there's some answers already there. You should see this. Do you see this in Full Everywhere? Open your app. You see this thing? Touch it and answer these. Touch where it applies to you in 3 categories. How big was your high school class? And how much chemistry have you had? how many years of college have you had? So fill those up. We'll take a minute to do that. Just want to get to know each other. Some of you are improving your aim. It is kind of small on your phone. Okay, so I think we can see already that there is broad diversity here. There's no one kind of student in Chem 1. We have all kinds of different experience in college level classes. We have a lot of different experience in chemistry. Some of you had AP classes. Some of you answer, what does AP stand for? So all kinds of variety of students in this class. And that's true for freshman chemistry in general, and it's especially true of the summer session, because summer session is open enrollment, and students who are not, as you know, enrolled in Berkeley can take the summer session. But we are going to do exactly what I do in the fall. So it's exactly Berkeley Chem 1A. No holds barred. So you're experiencing what we do at Cal. Okay? So we are going to start right off with one of these chem quizzes. We're going to do these all the time. And there's a couple things you should know about them. One, they're learning experiences. You're not supposed to know the answer. You're supposed to talk about it with your peers and respond with your device. And we talk about it and we treat it as a learning experience. It's part of the learning experience we do. So there's interactive learning here. We're going to do two right now, totally cold. I haven't said one thing about chemistry yet. So that's okay. This is going to give you the feeling of really not knowing what's going on. But for this first one, we'll have a demonstration of what's going on. So we have 3 balloons here, and oh my God, Karen is amazing. She made them the same colors as the slide. Will you ignite these for us, Karen? This is Karen Chan. You'll come to be your favorite person, because when she comes out, something will probably explode shortly thereafter. So what we have are 3 balloons, and we are actually going to ignite them for you now so you can see what goes on and you can respond to this question. So the first is a balloon filled with hydrogen only. Hydrogen gas reacts with oxygen gas to form water, and it releases energy when it does that. So Karen, if you'll do that, she'll ignite it with a flame, get the reaction going, and then it will go very rapidly to form water. We won't see the water. Isn't it cool? So that released some energy. Now we're going to ignite an oxygen-only balloon. So we did hydrogen only, but there's oxygen in the room. So there was oxygen there for it to react with. We'll do oxygen only and see how that reacts. Essentially, the balloon just popped. There wasn't any reaction at all there. That might be surprising to you. Here is a mixture of hydrogen and oxygen in the same balloon, but the balloon is the same size. So that means there's half as much oxygen, or there's half as much hydrogen as there was in the first one, but a mixture of the two in the same balloon. Actually, oh, Karen already did it. You might want to cover your ears. This might be loud. Go ahead, Karen. Okay, so do you believe your ears? Go ahead and respond to that question about what releases the most energy using your pole everywhere. The what? Oh, now it's ready. You ready? Are you guys responding?
Yeah.
Okay, there might be something that I have to do to see the responses here. But I don't know what it is. We saw them. Oh, here we go. Okay, that's good. Once everybody, probably have responded, I'll look at the responses there. Many people think that that released the most energy, the hydrogen and oxygen balloon combination. I'm not too surprised you thought that. But this might surprise you, the actual answer. The first balloon released the most energy. So we'll talk about it more. I'm going to leave it as an open question because we'll get to the answer very shortly in the lecture. But essentially, it's okay just to be surprised by that right now and be primed to figure out why that is the answer in a few minutes. This one, when we ignited just the oxygen, some of you might have been surprised that that didn't react at all. Because when you watch movies and TV, there'll be, oxygen gas or oxygen tanks, and somebody will get a match near it, and it'll just explode and, destroy whole buildings. The origin of Deadpool. Anybody seen the Deadpool series? He's trapped in a I don't know, some evil villain has him trapped. He's in a hyperbaric chamber. They fill it with oxygen, and to escape, he has like a match on him or something. He's able to get a match into his mouth and strike it, and he blows himself up to get out of it. But it's just oxygen in the chamber, and it would have done what this would have done. The match might have flared a little bit. Ooh, some oxygen, but that's it. You need some fuel to burn things. Oxygen is a reactive substance, but it reacts with other stuff. There has to be stuff in there for it to burn. Oxygen itself is not a dangerous explosive gas, but it makes other things burn. So it's something to be aware of. And we'll talk about it all the time in this class, because popular media warps everybody's understanding of science because they always do it wrong, for effect, of course. So you have to sometimes unlearn what you see in class on TV or in the Marvel universe for sure, so that you can understand the science below it. We have 3 people in row H. You guys in row H, come in, join us in G or forward. We're all going to talk to each other during this class. So Karen is ready. Actually, yeah, go take your time, Karen. We'll keep going here. So now I'm going to use a word that you might not even have heard. But again, we're doing chem quizzes. You're not supposed to know anything. We're doing it cold. But a lot of you have had AP chemistry, so you've heard the word before. If you haven't heard the word before, that's okay. We're going to talk about this amongst ourselves. Say I had a deck of cards and I forgot to bring one. Let's say I had a deck of cards and I was holding it here stacked in a tight stack. And we consider the entropy of that situation. You guys coming in, row G or forward, please. You'll have to squeeze in and talk to somebody. You'll be holding it in your hand. Some of you might not know what this entropy thing is, so you're going to have to talk to your neighbor in a second. Maybe they will, but you'll talk among yourselves. I'm going to do something. I'm going to spray that deck of cards around the room and let them fall to the ground, and then they'll be all over the ground. So I have 2 states, one of them packed in a deck, one of them spread around on the floor. My question to you is, how did the entropy change from stacked to on the floor? Did it increase, decrease, or stay the same? So now turn to your neighbor and discuss that. And talk about that, introduce yourself to your neighbor, talk, and when the GSIs are here, they will be in your little groups and they will be talking to you Wednesday and on. but go ahead and talk to your neighbor about that and see if you can figure out what that is. Maybe ask your neighbor, what is entropy, if you haven't had chemistry before. What did you guys think? Increase?
Yeah, so entropy
You think
is
increase? Increase? So you've had some chemistry? You've seen this
disorder.
before, you've heard this, yes.
What do you think the answer is?
They're both.
Why do you think
What you
that?
put in
Because entropy is like the negative randomness, so if you like spread around, the randomness increases.
Think about it that the deck of cards is already in random order. Like that the cards in a stack are already in a random order. So how does the randomness change if you just throw them around?
I'll start the poll so you can respond now. So go ahead and respond. You can keep discussing, but you can respond if you'd like. And very quickly, it looks like increased is extremely popular. There's some decreased, some sames. What is the answer? We'll always discuss the answer. Sometimes we'll vote multiple times. What is the answer? I think sometimes I might have to do that. You may be surprised that same is the answer. And that's going to make some of you go, what? My school's going to do that all the time. But you're in college now. We're going to get to that in a minute. We're going to leave that as an unanswered question. You can ask your GSI, but why is that the same? Very shortly, in a lecture or two, we'll get to understand why that is. But I'll give you a little preview. Those cards on the floor are just sitting there. And they were also just sitting there in my hand. There's more to entropy than you learned in high school. So here we are. We did 2 chem quizzes, and basically we mostly got them wrong. But we are also a tremendously diverse group. Some of us had AP chemistry. Some of us probably got a 5 on the AP chemistry exam. Some of us haven't had chemistry yet, or maybe they had it as a sophomore and maybe they went to the music academy, so it wasn't great. Maybe their high school, some of you went to a high school with a gravel parking lot. Maybe some of you went to a high school with a golf course. You have a tremendous diversity in this room, but all of us are on a pretty level playing field here. We've all got something to learn. So we didn't do this to say, neither you guys don't know the answer. We did this to say, hey, we're all starting at the same place. And we're going to learn what the answers to these things are. And I'm very excited to help you do that. And I hope you're excited too. And we're going to go through 8 weeks of understanding these concepts and learning about the conceptual nature of chemistry. We're going to teach this at a very conceptual level. And my goal for you, many of you are not going to take another chemistry class. There's chemistry required for a lot of majors. My goal is not to convert you into chemistry majors. My goal is not to weed you out. So some of you get to go into science and some of you don't. My goal is to include you, welcome you into science, and when you leave this, you should be ambassadors of science. You should be able to talk to your friends and neighbors about science. You should go out into the world and explain the universe to people who, unfortunately, these days need that explanation. So we're gonna form warriors for science. Ambassadors is a better word. We're not going to be aggressive about it. And we grade this class on a straight scale. Everybody can get an A. I don't care. That would be great. I would love to give all A's. It's a straight scale. There's no competition. If you went to UCLA, God forbid, Chem 1 is on a curve, and they say the first day the top 10% of you get A's, the rest of you are screwed. We don't do that here at Cal. Chem 1 is to welcome you into science, not to weed you out of science. I want you to join at whatever level you want to join. And I want you to be inspired by it. So that's our goal. So what is science? We've already said, we do not know is the foundation. We have to accept we don't know what the answer might be. And something might happen tomorrow that revolutionizes what we think. That's happened recently when the James Webb Telescope started taking pictures. And we go, oh, crap. Those galaxies shouldn't be that well formed. Damn. So we have to be thinking about what our fundamental understanding of the universe is, and it's changing today because of experiments we're doing today in the Webb telescope. So those really smart astrophysicists that have been babbling on about the Big Bang and how old the universe is, whoops, they're reconsidering right now because of new explanations. And here, I encourage you to read this book, if you'd like. It's called Sapiens, A Brief History of Humankind. Fantastic book, easy to read. I was reading it on the Kindle, and they let you do this cool thing where you can just highlight a passage and make a quotey thing. So there are no gods in the universe, no nations, no money, no human rights, no laws, no justice outside the imagination of human beings. We create all that stuff in our heads. None of this is in nature. So we need to understand when we're scientists that we can't be distracted by this stuff because we made that stuff up. And you know there's hundreds of versions of it. So all this is off limits in science. What is on limits is what we can look at and see happen. So here it is, a roadmap to the entire class. We're going to bring this slide up many, many times, and we're going to look at all the various aspects of chemistry, and they're summarized here. There is the states of matter, gases, liquids, solids, chemical reactions and how they react, the kinetics of how they react, the quantum mechanics of the structures of the individual atoms, the energy is what we'll start with, the energy differences between states. All of those things, that's the era of thermodynamics, all of those things we'll talk about in the class, and we'll bring this picture up essentially every day and see where we are on the roadmap for Chem 1A. And you'll get to understand all the parts of this diagram. Many of you recognize already chemical reactions. Many of you have probably seen this or pictures of molecules. We are going to learn about them very, very carefully. So speaking of energy, Karen has two more balloons. She has some reactants that will go to products. And the reactants, in a sense, are higher in energy than the products. So when you go from reactants to products, energy is released. That's what happened in the first two balloons. Those balloons were filled with hydrogen and different amounts. Same thing here. We have a different hydrocarbon. You know which one we have here? It's butane. Butane in the two balloons. But the same situation, this one has half as much. And the rest is just filled up with nitrogen, air, essentially. So again, this is the same situation. Twice as much butane in that balloon as that balloon. And Karen will ignite them in sequence. And let's see what we see in here. You don't have to, I believe, cover your ears for this one, but I think you will feel it. That's a tough balloon. Ooh. So you felt that, didn't you? That was a wave of heat. Contained. Karen was ready for everything. So now we're going to do the same reaction, just like we did with the hydrogen. We're going to do a mixture. In this case, we didn't add pure oxygen. We added air, not very much oxygen. Mostly pure, air is only a few percent oxygen, 20%. So most of that is nitrogen gas, and the nitrogen is just there to take up space. But half as much butane. Go ahead, Karen. There we go. Now, I think those of you in the back row, maybe, in the front row, it's hard to tell, but what we did is we reacted essentially one volume of butane, and then we reacted half that much, half a volume of butane. The half volume, and I hope you could feel it. Let's see, tell me if you could. The first one, you should have felt a stronger heat wave than the second one. So when we do the reaction this way, you would have answered correctly. The one with the pure substance, twice as much of it, released more energy than the one with the mixture. And that's a fundamental property of science. Energy is an extensive property. It depends on the extent of the system. How much is there? How big is the system? In one, there was 2 volumes of butane. In the other, there was half a volume of butane, half as much butane, half as much energy. Energy depends on what is there and how much of it. So if you have 2 hydrogen molecules, those will release half the energy of 4 hydrogen molecules when they react. Same thing with the butane. You do that molecule by molecule, as if they were in a gas. Other features of this diagram, we'll talk about catalysis and the effect on this diagram. We're going to start with what we just saw, the difference in energy between products and reactants and products. Here are the reactants at this energy level. Here are the products at this energy level. There's that much energy that was released when the reaction occurred, and you felt it. Okay, that's number 1. So, on to number 2. So, we're working our way down the syllabus. We've already done the first lecture, Introduction. On the syllabus, we're already into the second lecture in the syllabus. There are no homework questions associated with that first one. It gives you an idea. You will use it. Here, and I won't leave this up for very long. You have it in your notes. Here are the things you should be able to do after you've heard and studied this material. Right after I say it, you might not be able to do all these things, but we'll practice many of them with chem quizzes. But every homework problem is matched to these learning goals. So when you're done with this, understanding this material, you should be able to rank relative energy states of a system. And you should be able to put them in order of increasing or decreasing energy. You should be able to track changes in state functions. If it's bold and italic, you should be able to define the term exothermic, endothermic, state function, work, heat. So this, in front of every lecture, is a guide to what you need to know by the time you're done with that material and the homework associated with it. We won't beat on them in real time. So here it is today. We're going to start here talking about this part of the roadmap to Chem 1A. Energy interactions. So, what is energy? It's an extensive state property of a system. Extensive, we already know. It depends on how much of it is there. It's a state variable. What does that mean? It's very simple. A state variable depends only on the state of the system right now. Temperature is a state variable. What's the temperature right now? Volume is a state variable. How much of it is there right now? Very simple, fundamental properties of the system. Some of them are state variables because they only depend on the state right now. Energy is one of those. So that's a good way to absorb this whole idea of energy is a state variable. It only depends, the energy of the system depends on the state of the system at this second. If you change the state of the system, there's a different energy that depends on only that state. It doesn't depend on anything between. It doesn't depend on how you got from one to the other. That's the important part. If you have two states, you don't have to know what happened in between. State variables are like a blinder function. You look at the state, put the blinders on, put the state changes, you open your eyes, and you see the new state and the new energy, and you don't have to know how somebody took you along that path to get between them. Okay? And I'm sure you understand that with temperature and volume. You could take the volume, say you had the temperature of one state here and the temperature of a state here, and you close your eyes and somebody heated it up to 1,000 degrees and then lowered it back to this temperature. When you open your eyes, all you can see is the difference between them. You can see this temperature, and that's it. State functions. So, how do we define energy? It's relative. This is the thing that you should be thinking of all the time. Energy is a property of the system, but we hardly ever determine an exact number for it. Especially in this class, we just compare it to something else. 99% of the time, we're talking about energy differences between two states. This separation in energy is what we're interested in. That's how we define the energy. We define the energy relative to another state. So, here's an easy way to think of it. Maybe, it's intuitive. Can a system do work? Can you extract some energy to do work? Can you lift something? Can a balloon expand and move something? Can a piston expand and move something? If there's movement in a concerted way, that's work. Very simple definition of work. Organized movement. If a system can impart organized movement on something else, then it had more energy than that other thing that is exerting the energy on. It was able to release some of its energy. So you can say, that thing has energy. It can do some work. And when it does the work, I think you'll probably understand, it uses some of its energy. So its energy goes down because it used some of its energy to do work. So you can have a flowchart of sorts, of course. Yes, the system can do work. Well, then the system has more energy than the surroundings if it can do work on the surroundings. And if not, then the system has less energy than the surroundings. And now we're talking about systems and surroundings. So the system will often very precisely define. The system in those butane balloons was not the balloon itself, it was the butane molecules within that balloon. They were held in one region of space by the balloon, but the system was just the butane molecules. You could add the oxygen molecules that react with it. Call that your system, a mixture of two molecules. Even though there's all kinds of other stuff there, you can pick out and draw a boundary, even though if you have the butanes and you had to draw the boundary, you'd have to eliminate the nitrogen and the other gases in the air and include just the oxygen and the butane in your circle that's defining your system. That's okay. We imagine what the system is. You don't actually have to be able to produce it in the laboratory. You have to be able to imagine what the system is. The surroundings is everything else. And normally it's just the local surroundings, what's nearby. Okay? So in this case, energy of the system is bigger than the surroundings. In this case, the energy of the system is lower than that of the surroundings. How do you express that? You can express that on a graph very simply. And we're going to do this all the time till you're sick of it. Here's one energy state, and energy in this class will have arrows pointing up the board all the time, and the higher on the board you are, the higher energy you have. Energy increasing. So the difference between an initial state and a final state, there are two different states of the system. That has an energy, that has an energy, and we put them right here with no other axis. Why? You should already be able to tell me. Nothing else matters except those two states. The state now and the state later, no pathway between them. You do not care how I got between them. So you can always just rank them straight up and down, vertically. We're going to do that all the time. And we can do that by an equation. The change in energy is always the final state energy minus the initial state energy. That has an energy, that has an energy. If I subtract that energy from that energy, that's the change in energy. And it's always the same. When you see this delta sign, that means take the state function in the final state, subtract away the state function value in the initial state. Final minus initial. So in this case, there's the initial state energy, the final state energy. This energy difference that we express in this distance is the change in energy. We'll do this all the time. So this could be a process, but it doesn't matter what the process is. All we need to know is the initial and final state. There's some pathway. We don't care. All that matters is the initial and final state. Now, we could be clever, and we'll do this sometimes. Since energy is all relative, and we don't have to often give a number to it, it's the difference that matters. We'll often arbitrarily say, well, let's just say the initial state was 0 in energy. That'll make the math easy all the time, because this one's always 0. So we will use standards and say, well, that's 0. We'll say, okay, this will be the 0 in energy, and we'll measure everything else relative to that. Because that's the idea. Energy is relative. It doesn't make any sense as a number unless you can compare that to something else. The number you have to compare to the surroundings to know if the system can do work or can release energy. So being clever and saying, oh, I'm just going to arbitrarily call that 0, then the energy change in this is the final energy minus the initial energy. Initial energy is 0. So the energy change here, delta E, is just the final energy state. Makes the math a lot easier. If you're writing computer code, wow, you just saved yourself a lot of lines of code by saying, okay, make that 0 and measure everything relative to that. Notice, if the initial energy is 0, then the energy of this state is less than 0. Well, I should have made that more clear. Let's talk about that in the relationship between these two. If this is 0, then this has negative energy. So there's positive values of energy up here and negative values of energy down here, if that's 0. That should kind of be obvious to you. But you get to this idea where you put a negative sign in front of energy. Now, there is no such thing really as negative energy. If you see the negative sign, it just means it's lower relative to something else. So it's lower than the 0 energy state. All the negative sign would do is allow you to take this one, which is 0, and put the final below it on a graph. You know that positive numbers are above 0 and negative numbers are below 0. So if you know E final was negative, then you could have put final down here below the initial in this case. And that's what we want to do. That was learning goal 1. Rank systems, draw them, put them on a board. And on exams, we will do this. You're going to be annoyed because on the exams, there won't be many numbers. You'll be drawing pictures, and you'll be telling me what's happening in a picture. You'll be arranging things from top to bottom, high energy to low energy. Why do we do that? Because I want you to conceptually understand this. I don't want you to plug 2 numbers into this formula and subtract 20 from 30 and get minus 10. That's boring, and it doesn't tell you anything. You can't go out and be an ambassador to the world. You could do that when you got in here. You could subtract 20 from 30 when you got here. It didn't help you go be an ambassador of science. So on the exams and on homework, you'll practice it. You will give us conceptual answers. You will rank things. You will tell us what they look like relative to something else. Another reason we do that is we know the internet exists. We're not stupid. Well, we have a big staff. No one has ever said, I'm not stupid. Or no one has ever said, Kubinec, yeah, I wouldn't call him smart. I usually get the other designation. But we have a big staff, and we understand that we're going to give you these exams online. We ask you, we in fact, we demand that you use the utmost academic integrity on your exams, and you do not Google the answer. But we do this so you can't Google the answer. Okay? So prepare to look at the homework, understand not just the question, but how we are asking it, so that you can answer it on the exam. Here, we'll do it right now. Which system has energy? So the system and the surroundings are here in 3 different organizations. Which one of those systems, is that the question, has energy? Which one would we say has energy by the definitions we're using? Can it influence the system? Go ahead, talk about that amongst yourselves, and we'll take a vote on that. Go ahead. Even now, Christina, you can talk.
What do you guys think? What's the thought process?
Well, this is asking the question that you do.
You said B or C? A? Why? What, the system's gaining energy?
I think so.
It's like it's doing, well, in C, like the system does work.
No, the surrounding does.
In C? Oh, in A, well, if A, yeah, the surrounding does work. In C, the system does work. I agree with C. But it's asking like which has energy. Energy is you guys have the right idea, but you're all in different places. So try to agree on one answer.
Okay, I'm getting a lot of good discussions here.
You could logically, well,
Let's
he's
turn
gonna
on
tell
the
you.
thing so you can actually vote on it as well. Sometimes I hide this until you're done, so the answers coming in don't influence people. a lot of us are thinking C. There's a couple of us for A. I will tell you by the definition we used earlier, and we can talk about what negative energy means. But what I want to get at here is simply here the system has more energy than the surroundings, and this system can do work on the surroundings. Now, in the big picture, maybe everything has energy. That's okay. So if you answered A or B, that's fine too. Everything might have some energy, but if we want to quantify, is this thing able to do some work? Does it have enough energy to do some work? This one does. These two can't do work on the surroundings because they are lower in energy. But don't get too bound up on that. If you answered A because you said, well, they're on an energy plot, so they must have energy, you're not very wrong. It's just a different way we were looking at it for this particular case. Okay? So I was looking for C, but like I said, you could have answered anything there pretty legitimately. I am gonna skip this, I think. No, we'll do it. Okay, now we have actual stuff. 10 liters of hydrogen, 20 liters of hydrogen, or 30 grams of hydrogen. Can you arrange those state 1 or system 1, system 2, system 3 relative to each other? Again, we could say they all have energy, but we'll be able to rank them relative to each other. Can you do that? So talk about that amongst yourselves and see if you can come to a conclusion on that.
Because two are we can't really compare what we think. So we can compare the first two.
Yeah.
So what is that?
Yeah.
So you used to let's say 2 has more energy than. Right. See if you see it now. We're stuck. We just choose
More matter.
But you can get close to the answer. 2 being greater than 1 is true B and C, and then it is the reason we put this up is very shortly when you count 30 grams relative to 20 liters. Yeah, you have to so it's kind of 2 grams a minute. That's a ton more. 16 more. Way more than 1 gram is 20. That's really more. Okay, go ahead and vote if you like, and I will hide your answers until the vote is complete, so we don't influence anybody. Okay, I think you were all, is the mic on or off? You were all kind of ready, so let's just see what you're thinking. About equally split between B and C. Actually, there's probably more for B. There's supposed to be a way we show the percentages. I'm new with this quizzing thing, but it'd be nice sometimes. I'll look at that later, and we could look more precisely at what you're thinking, but maybe just a few more for B than C. And I like that. That's what you should have been doing. This one we just did like 3 times in a row. We did twice the volume of hydrogen as in one case and the other. and we saw, yes, energy is an extensive property. If you have 20 liters of hydrogen, that's higher energy than 10 liters of hydrogen. But all that allowed you to do is pick either B or C, because in those cases, we had system 2.
Exactly.
Oh no, wait a minute. That allowed you to pick this. 2 is bigger than 1. Here, 2 and 1 are the same, so you couldn't even pick that, could you? 3 is a mass. And obviously, again, remember, you're not supposed to know the whole answer. You're supposed to talk about it. Some of you might be very clever, and you know the relationship between a mass of a gas and its volume. And you might have been able to say how much hydrogen is there. But we can talk about gases in terms of their volume or their mass. And by the end of this class, that'll be the same to you. You don't care if I give it to you in volume or mass. You'll be able to just switch between volume and mass in your head almost. So the question is, which is the case? But I think you would have picked B, because in B, at least 2 is greater than 1. And here in C, 2 is equal to 1. And you know energy is an extensive property. It depends on how much is there. And it does turn out 30 grams is much more than 20 liters of gas at room temperature. But again, you didn't need to know that to arrive at C. Or B. There it is. So I'm just reviewing. There it is. 2 liters here, 1 liter there. 10 liter. Which released the most energy? The hydrogen balloon. Why? Because there was twice as much energy as here than here. And it might still be bugging you. Why the hell did that frickin' blow the doors off the room then? Why did it?
Because it had.
Anybody got an idea? Yes.
Because it had oxygen.
It had oxygen
Like emphasizes the reaction.
And it what?
It had oxygen in it, so it kind of emphasized the reaction, and like the heat was more.
Yeah. So the response here is the oxygen was already in there, so it emphasized the reaction. The scientific word for that might be that the reaction could go faster because the oxygen was already there, mixed intimately. The first balloon, the flame had to break the surface of the balloon, and then the hydrogen had to mix with oxygen in the air and then react. That happened very fast, but it would happen faster if the oxygen's already in there, especially if it's pure oxygen. So it didn't even have to sort out the nitrogens from the oxygens. It could just go. So the fact that it could just go is the answer. This is the difference between energy and power. Power is how much energy you use per second. This thing called power is energy per unit time, seconds. So it'll be joules per second because we use energy in the unit of joules. So, and you kind of know this intuitively probably already now that we've said it. Oh yeah. If you want something to be powerful, that means you use energy very fast. It doesn't matter. Think about it this way. You're a bomb maker. You want to blow something up. You get a very high energy system, but if it takes 3 days to release the energy, it doesn't knock the building down. You want to release the energy in 1 second. The denominator. You want that to be small. Few seconds gives you big power. The reason the second balloon rocked the room is that it happened in a microsecond rather than a couple hundred milliseconds. So that's all it takes to get power from energy. Use it faster. Okay. So we often use this word stability, and I don't like it very much, so I won't use it very much, but it does have its place. So, but it's also a common word in the English language. And you'll come in here, and when I use a word, I'm going to use it very precisely. And I'm going to expect you to know the definition of the word so you know what I'm talking about. In a sense, a lot of times I'm almost going to be speaking a different language because you might use a common definition of stability, and I'm going to use a very precise one. And that's one of the reasons some days you'll be maybe a little lost, and the words coming out of my mouth will be pretty sure they're English, but they're not resonating with you. It's because of the precision of the way I speak. I won't mix up energy and power. I won't mix up heat, work, energy, temperature. I will use the exact definitions of those things, and you guys can't define them precisely yet. So you're going to have to catch up with me. But you will by the end of the class. Stability is one of them. So let's do something fun. Just tell me, word cloud. Write a word in Poll Everywhere. When you think of stability, what word do you think of? And anything. Don't think of me as your chemistry instructor right now. Think of me as your therapist. What is stability to you? Give me a word. Oh, I love that. So we got balance. We've got homeostasis, for God's sake. Consistency, equilibrium. Wow. Yeah, look at that. Balance is still really big. Zero. Peace. I'm glad somebody said peace. Consistency. Balance. Fantastic. So we see where we're coming from. You guys think of stability and balance, stability and peace. And indeed, that is so how it's used colloquially. Colloquial means in the general conversation. But in this class, of course, I'm going to use it very precisely. And this is one of those times where you'll be listening to a chemist and they will say stable and you won't know exactly what that means, so it'll go over your head and then you'll miss the next part because it mattered what stability was. Okay? So what do I mean by stability? Let me take a screenshot of that. That's cool. Oh, I can. Anyway. Capture. Cool. Open in the whiteboard. I think that's saved now in the whiteboard. We'll post that on the website because that's kind of cool. And it's cool that, I can move it around, but if I have a pen, balance was what we thought. Well, no. Okay, so moving on. Okay, well, let's talk about stability then. Again, all stable means is relative to something else. Do you have more energy or less energy? Stability by itself doesn't mean anything if it's a single system. Stability, when I use the word, means I'm comparing it to something else and it's lower in energy. That's it. So I'd like you guys to think about that. Here are some common things. Oatmeal. Which is more stable? The stable things are lower in energy than the higher things. So stability means I'm low on the energy scale, less stable, high on the energy scale, and I need at least one other thing on the energy scale to tell you if I'm stable. I'm always stable relative to something else. I have lower energy than something else. So here are 3 states of oatmeal. Oatmeal in instant oatmeal in the grain packet Karen has some boiling water we were going to make oatmeal. I forgot to bring it. But if I had some instant oatmeal, I could put that hot water in it, and I could make the delicious breakfast treat that I'm sure you all have enjoyed. But if I let that breakfast treat sit around, it turns into this, stuck on the bowl in the morning if I don't wash my dishes. So the question I have for you, can you arrange these three states relative to each other in terms of stability, relative to each other in terms of energy? Which is the highest energy, which is the lowest energy state? And now we're going to talk about energy per gram, not overall energy. We talk about energy per gram because you don't know how much of each one of these things is there. So a gram of this, a gram of that, and a gram of that. Energy per gram. How would you arrange? Very important thing I just did there. So don't let it go over your head. Now I'm talking about energy per unit mass. So I can compare things without knowing how much is there, which is what we'll do for most of the rest of the class. Okay? Go ahead, talk about that among yourselves and tell me what you think.
Yes, it makes it so you don't want something.
I'm saying when I said energy per gram, the amount doesn't matter. If you had a gram of each one of
Try to think about it in terms of stability. In terms of stability, rather than so much energy. So what did he say about less stability, more energy?
More energy. So it has to be like C.
Yeah, so I feel like
No, then it has to be A.
oh wait.
If it's less stable and more energy.
Try to think about it like that. Well, I mean, this is energy, but energy is directly related to stability.
So more than energy, less the stability.
I think, yeah.
Right?
I think C is right. I'm not sure, but that's what I think.
how much energy does it take to get
Yeah, three. Yeah, three's like nothing in there. Yeah, one. Yeah, I feel like this two has added energy and it's like already.
What are your guys' names?
I'm Ria.
Ria?
Yeah.
Okay, I will turn on the voting machine.
Shobha.
I hope.
C. Yeah. C.
I don't know why I can't turn on the voting. There it is. Okay, go ahead and respond. I would like to default to the answers hidden.
Oh.
And I can probably set that. But I didn't do it this time, and people are already liking C there. So let's talk about that. You're thinking C. You're thinking number 2 is a high energy state. 1 and 3 are below that. I like that. Let me see if I can tell you what you were thinking. You're saying, I have 3 things, they have different energies. What do I know about going between the energy states? Well, how do I get from this one to this one? I add boiling water, I cook it. I put energy in to get from this one to this one. That's going up in energy, up on the energy scale. So 2, to go from here to here, put energy in, and I get the yummy breakfast. That looks like this, and that looks like, is that the only one that has 2 above 1? Oh no, here 2 is above 1. This. Oops, there's the answer. So, what about this one? How do I go from this one to the other 2? Well, it's hard to go to that one, but to go to this one from stuck on the bowl, and you, like probably everybody has had this experience, you don't want to leave the oatmeal bowl overnight because you know how hard it is to get that stuff off the bowl, how much energy it takes to get back to soft soluble oatmeal. Once it's been cooked once, it turns into the most powerful adhesive known to man. And there's the energy source that will do this is yet to be discovered. This is the lowest energy state because it takes the most energy to get back to the other 2 states. So you have a different appreciation already for energy than you did when you walked in the room. Has to be relative to something else. Do I have to put energy in to go there, or does energy come out when I go the other way? Though that's how you measure stability. This is the most stable state of oatmeal. Now I've used it in the precise sense, haven't I? This is the most stable state of oatmeal. Why? Shout it out for me. Why?
Lowest energy.
It's the lowest energy relative to the other one. Okay? That's the stable state of oatmeal. And in the universe, everything goes to the most stable state over time. Because it's the lowest energy. Everything tends to release energy over time. So everything tends to go to the lowest energy state. That's another reason we call it stable. That's how we encounter things, because if they've had enough time, that's where they end up. And it's stable because they don't want to go anywhere else. It takes energy to go somewhere else. That's why you're stable. Okay? So there's some energy landscape. Energy landscape. There's stable states along the landscape, but this one is higher on the landscape than this one. And this is in the lowest valley of the landscape because it's lower energy than this one. And oatmeal is free to go between the 2 if there's enough energy. But if it's free to go anywhere and it's switching in between the 2, what will happen? Well, once it gets here, it's hard to get out. So it's going to accumulate here. If it can switch in between all 3 of them. It's not likely to accumulate in the highest energy state. It'll accumulate in the lowest energy state. And we know, so we could talk about all the oatmeal in the universe being trapped in this state. If we wait long enough, all the oatmeal should end up in this state. It would be called the oatmeal death of the universe. All the energy, all the oatmeal is stuck in this state because it's the lowest energy state. And there's not enough energy in the universe to get it out of there anymore. In fact, it could lead to the entire death of the universe, because if all the oatmeal is being trapped in this state, oatmeal is just an organic compound, so we keep growing it and we could keep putting resources in to grow the oatmeal, and it keeps ending up there. And pretty soon, all the matter in the universe is trapped in the lowest energy state. It's the oatmeal death of the universe. And here's something interesting. You notice these 2 pictures these are from the internet. I just Googled cooked and uncooked oatmeal. I also Googled oatmeal stuck on bowl. There was no, So the rule is everything is on the internet. I could find no picture on the internet of oatmeal stuck on bowl. This is my bowl. I had to take a picture of that to put it on there. And you got to ask yourself, why is that? Come on, everything is on the internet. This is like one of those conspiracy theories. Why is everything on the internet except oatmeal stuck on bowl? Well, because there's some force out there that doesn't want you to know about the oatmeal death of the universe.
Wash it before they have the chance.
It is, who knows what that is? There's some mysterious force. It almost makes too much sense. You can't find that picture because there's a cabal. That's what Q is. It's a conspiracy theory. Q is preventing you from knowing this. So what is Q? I think now you know. What is Q? There's our exploding balloon and other stable states. What does Q stand for? Who is hiding this from us? Who does not want us to know, don't change stuff into oatmeal? Oatmeal is not the evil. Who would be hiding that from you? Well, that's what Q is. That's what Q is. It's that guy. All right, we will see you tomorrow. Have a good afternoon.
That's a good one.